welcome to the Home Energy Challenge, part of STEMfest Knox 2016. This is our inaugural effort with the Home Energy Challenge with STEMfest Knox, and we're very proud and happy to bring this challenge to the county's middle school and high school students and their teachers and mentors. So, my name is Holdener, and I'm on the faculty at Kenyon College, one of the sponsors of STEMfest Knox. And the other sponsors include Mount Vernon Nazarene University, the Central Ohio Technical College, Spy Spot, the Science Place-Based Initiative right next door here, and the Works down in Newark. And I also want to give a shout out and some thanks to some of the good people down at Owens Corning who helped me out in preparing these materials. All right. Now, what am I going to do today? Well, I'm making a presentation on the Home Energy Challenge. We'll have a statement of what the challenge is, and we'll give some background information on the science and some of the specifications of the materials, technical specifications of the materials, but only at a pretty basic level. There are two levels to the challenge. There's one for middle school students, and the high school students have to do a little bit more. I won't be going into that, but we can go into that with follow-up questions and follow-up contacts. The challenge also requires the groups to make a presentation on the day of the event, and I will say that that event occurs on Saturday, February 27th, 2016. And I will also talk about the requirements and things you should be considering for that presentation. All right. The Home Energy Challenge is really quite exciting, and it's a very significant task that most of us has faced, maybe not as individuals, but parts of families, but it also is a task that we have to tackle as communities and even as our nation. The challenge really presents a problem that is, it's an effort that we have to deal with as part of our national energy policy. And the significance and importance of that and the weight of that really comes out if you just look at the very two opening sentences of the challenge in the packet that you've all received. They read, and this is from the paragraph on background information, approximately 40% of U.S. energy goes into heating and cooling of residential and commercial buildings. Minimizing thermal losses is a huge opportunity area for global energy efficiency. So I think that really sums up what the challenge is and why we're giving it to you. Groups who take on this challenge will be provided with the following materials. You'll have a model structure, a model of a home or just a building if you want. Some insulating materials, got some fiberglass foam insulation, some foam sheeting. You've got some material, cardboard or cardstock that is representing drywall that will be placed on the inside of the structure. Some scissors for cutting that, and some materials for attaching the insulation and the cardstock to the structure. All right. Your task, in a one sentence nutshell, is to install these insulating materials into the model home to maximize the thermal efficiency of the structure. There you have it. Now, the structure, once you insulate it, put it together to your liking, needs to be turned in the day before the event. So on Friday, February 26th in the afternoon, you'll have to bring this in, and that evening we will test it. We'll put it on a table, and we will insert a heat source in there, and we'll measure the total energy required to maintain an internal temperature inside the structure for a specified length of time. That is the model portion of the challenge. And then, of course, you have the presentation on the day of the event. All right, now I want to get started with some of the science, the ideas behind the challenge. But before I do that, I want to get started, but I'm not going to yet. On page 16 of the packet, there is a list of resources, science, technology, engineering, and mathematics resources. I have purchased some of these, looked into some of these. I encourage you all to do so as well, to make use of those sources and also to find other sources, other books, other resources source of information that you will want to look into includes professionals in your community, in Knox County. Go find mechanical engineers that design heating and ventilation systems. Go find people who install them in homes and commercial buildings. Go find home inspectors who walk into existing homes and look for these materials in those existing homes and evaluate them for their efficiency. You'll want to use those people as resources when you're putting the model together and insulating it, but you'll also want to talk to them about their career choices and how they use the knowledge in their jobs, in their professions. That is part of the presentation. Okay, some definitions. Always got to have definitions. Heat. Heat is a form of energy. It spontaneously transfers from a system, such as a home or a model home, to that system's surroundings, okay, to the outside. We'll talk about heat transfer in a little bit more detail later. Temperature. Temperature is a comparative measure of how hot or cold something is. It's measured with a device called a thermometer. You've probably all seen those. Temperature can be measured in a variety of units, the most common of these being degrees Celsius, degrees Fahrenheit, or Kelvin. We'll want to stick with degrees Fahrenheit for our challenge this year. Temperature is often thought of as a measure of the movement of the material, the particles that make up a material, atoms and molecules. Think about the temperature of, say, a wall, a material inside of a wall. How fast are the molecules inside that wall moving around? Temperature of the air in this room. How fast are the molecules of air moving about in this room? The higher the temperature of the wall, the higher temperature of the air in this room, the more energy those molecules have, the atoms have, and they'll move around more. Okay. A British thermal unit. Okay, that's another unit or another term you're going to see in the packet. That's often abbreviated BTU, and it is actually a unit of work. One of the things you can do with temperature is you can perform work with it. If you have a pound of water and you raise the temperature, you add heat to the water to raise the temperature 1 degree Fahrenheit, you have done 1 British thermal unit of work. Okay? Yeah. Now, you'll often hear equivalences of BTUs given out to give you an idea of what that means. I don't have a wooden matchstick with me, but if I did, if you burn a wooden matchstick down all the way, that gives off the equivalent of 1 BTU. Okay. A little bit more exciting example, a glazed donut has about 700 BTUs equivalents of energy inside of it. A 1 pound mass of coal has about 10,000 BTUs of energy locked up inside of it. It doesn't taste as good as the donut, though. All right. Now, I want to pause here and make a little statement about units and British thermal units in particular, because one of the things you might find when you're doing your explorations and looking for other sources is one definition of a BTU might be different than another one when you're looking. This can come about because, well, the technical reason is because water, when you heat it up by 1 degree Fahrenheit, well, the energy that requires is different based upon the temperature, the initial temperature of the water. And certain people, in the US we use 1 initial temperature, in Canada they use a different initial temperature, in Europe and England they use a third different initial temperature. So you want to be careful to understand your sources. If you see discrepancies, it may be related to that. And keep track of units if you need to make calculations for part of your challenge. Always keep track of your units. Okay, heat transfer. Heat transfer occurs by typically 3 different ways. The first of these is conduction, and this occurs in solid materials in which the heat flows from one part of the solid to another, and it does that by moving along with the atoms and molecules in that solid. They are relatively stationary, but well, let me give you the common example, that of a metal pot with a metal handle. You put that on the stove and you turn on the burner, and of course the pot heats up, maybe you're boiling some water inside of there, but the handle will start to heat up too, and the heat will conduct up the metal handle. If you grab it at the wrong moment in time, when it's hot, you'll burn yourself. If you, well, let's see, let me draw a cartoon here. I was going to do this. Let me draw a little cartoon of a room, ceiling, walls, floor, okay? And now I'll just zoom in on a portion of the wall here. So just sort of do this. Zoom in on that wall there. If the interior temperature of this room is 70 degrees Fahrenheit, and the outside temperature is 40 degrees Fahrenheit, we've got a heat difference between the inside and the outside, and heat is going to move through there. It's going to want to escape. Inside the wall, so if this is the inside of the wall and this is the outside of the wall, we'll have molecules over here that are at 70 degrees Fahrenheit and molecules over here that are at 40 degrees. And the molecules over here are moving about and they're bumping into each other and they're transferring heat because of that motion to the molecules on the inside of the wall, and that will continue to move through to the outside of the wall where it can escape to the outside. This another example or another expression of the problem that we're trying to address here. In maximizing the efficiency, we're going to eventually want to insulate that wall. Okay, radiation. Radiation is how the sun's heat energy gets to us here on Earth. It's also the idea behind the fact that you can't stand too close to a bonfire. If you're outside and toasted marshmallows, you can't get too close to that fire because it's radiating a great deal of heat. So radiation is a way that heat gets transferred through space. Hot objects always give off heat radiation, unless they're at absolute zero, but that's the definition of not hot for physicists. They give it off in the form of infrared radiation that just radiates out into the space. The total amount of infrared thermal radiation depends upon the temperature of the body. So as it heats up and gets hotter and hotter, it'll give off more thermal radiation. One of the best ways to think about this is, let's draw, I can build a bonfire in our little cartoon of a room, but we'll put a wood-burning fireplace in here, okay? There we go. And we'll fire that up and we'll stoke a good fire in there. All right, now, when that metal in this wood-burning stove heats up, it will begin to radiate heat as infrared thermal radiation out into the room. And depending upon the temperature of the stove, you may not be able to get too close to it. You certainly don't want to touch it. All right. Now, the final way that heat can be transferred is by convection. Convection occurs in fluids. And fluids, in this sense, can actually be either liquids or gases. But for obvious reasons, we're just going to limit our discussion here to gases, such as the gas in the air in this room, in the model, and in the room right here. With this wood-burning stove, we'll keep that example there. Erase my heat given off as radiation. And we've got molecules of gas in that room, and the molecules of gas above the stove get heated up. So they start out cool, and they get heated up, and they become hotter, and as they gain heat, temperature rises, they start to move about more, and they move about and away from each other, and that packet of air, if you want to consider it that, gets less dense than the surrounding air, and it starts to rise up toward the ceiling. Hot air rises, just like hot air in a hot air balloon. Hot air rising up above a candle that prevents you from putting your hand over it and leaving it there for any length of time. As it hits the ceiling, it spreads out over the rest of the room, and as it does that, it starts to cool. A little bit cooler color here, but eventually it gets so cool that it will become denser and start to sink down, change colors, okay? Now, when the hot air rises above the stove, we can't just leave an empty space there, so cooler air will move into that empty space, and then it will heat up and rise and spread out over the surface of the ceiling and drop down as well. So in this sense, in this manner, we create, with different colors, a convection of air, a convection flow of air around the room. And this is really the way a radiator, in spite of its name, heats up a room, is by warming air and having these convection flows of warm air circulate around the room. Okay, now, air can also convect and transfer heat inside a wall. I've drawn a very simple diagram of a wall, okay, but most walls are actually double thick, right, with some gap in between them, some air in between them, all right, and if you leave a wall empty such as this, and leave that gap of space between the inside wall and the outside wall of your home, that air then can convect and transfer heat from the inside to the outside very well. Okay, this is a problem. And with the materials that we've given you in the kits, you'll want to address that problem. The fiberglass insulation is designed, manufactured to have lots of little tiny packets of air instead of large gaps, large packets of air for convection, and prevents the convection inside the walls and lowers the heat loss that way. All right. Okay, another idea is R value. When you get these materials, when you start to look at the sources and investigate them, you'll see that materials are given an R value. And the R there stands for resistance. So an R value of a material is the resistance to heat flow within that material. The higher a material's R value, the better it is at insulating. So the wood in your structure has an R value of 1.8. The 1.5 inch thick fiberglass insulation has an R value of 4.2. So greater number, higher R value, better at insulating. The 1/4 inch foam right there has an R value of 1. For our purposes, the cardboard that we give you, you can just ignore that as an insulator. It has an R value of 0 essentially. Yeah. Now, let's think of an analogy that is all familiar to us. Clothing. If you go outside on a cold day in your bathing suit, you might be a little cold. Your mother might yell at you and tell you to put on some clothes. What are you thinking? So you'll go in, and if it's not such a cold day, you put on a t-shirt and you're fine. The t-shirt, well, I should say your body radiates heat. Okay, it uses heat by radiation to the world around us. You put on the clothing, you put on the t-shirt,